Welcome back, everybody. Dr. Schoffers here as we proceed in Chapter 19. Sometimes it's a good idea to think about where one has been and where one is going so that we have a goal. I'd like to highlight this briefly here with the slide I put together. Basically, we had a very important segment, 19.4, Introduction to Nucleophilic Addition Reaction. There were two key mechanisms, 19.1, where we have a nucleophilic attack under basic conditions, and then 19.2 using acidic conditions. The mechanism followed the patterns that you learned about in Chapter 6. First a nucleophilic attack, then a proton transfer. In the second case, it was a proton transfer and then a nucleophilic attack. I'm mentioning this because basically what we have done in the previous section, looking at all the oxygen nucleophiles, and what we're going to do in the next segment, and then there are going to be additional segments, we're talking about different kinds of nucleophiles, and we need to discern whether now we have acidic or basic conditions. So I highly recommend that you focus on seeing the patterns, how they repeat each other, and that way you won't feel overwhelmed as to like, oh, there's so much new material, when really it is just a different shade of something you have seen before. And you used your good curved arrows, you drew good intermediates, you understand how to calculate formal charges, so on and so forth. All right, so we, in the previous segment, focused on oxygen nucleophiles. We'll now have some rather complex and difficult material for nitrogen nucleophiles, but we can use our basic understanding of mechanisms and then do well. And many of you are doing really well, even though there's a lot of material to work through. So here we have now the beginning of nitrogen nucleophiles. We have acidic conditions, so that should ring a bell, ding, 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 ding. You will see on the reaction arrow, as shown in this example here, the square brackets means that there are different types of reagents that we can use that produce a proton to catalyze the reaction. So that's what the square bracket is about. We are dealing with reactions of aldehydes and ketones. Here, the focus is on now what is going to happen with a primary amine. And then there's a new word to add to your technical jargon. We're basically converting the amine to an imine. The overall conversion has to do with a carbon-oxygen double bond. Here we have it highlighted in green. Now converting to a carbon-nitrogen double bond, and here we see it. I like to sometimes highlight to understand how bonds are broken, formed and broken, to basically redraw the molecule. Now we'll encounter amines, and there is going to be a rich chapter of this as well in Chapter 22. So it's a kind of a preview where you will see the other side, everything focusing on the amines and the reactions they can undergo. Right now we're still concerned with aldehydes and ketones. Here we need to recognize that we have a CH3 group. Please make sure and be very precise as to how you connect something. You need to connect to the carbon, the nitrogen, and then we have two hydrogens. And I like to draw it this way because then I can better see how these two molecules now come together. Carbon-oxygen double bond is replaced with carbon-nitrogen double bond. The hydrogens are gone, the oxygen is gone, i.e. loss of water. We also refer to this as a condensation reaction. And then we form the imine product. We can also visualize this. Basically, here we are, we're getting rid of this. This is not a replacement for a mechanism, but for visualization how the structural features change. So we also need to know what constitutes acidic conditions, and there are a variety of sources that will accomplish this. On this slide here, we now have the mechanism. I would encourage you to pause, maybe walk yourself through, maybe copy it down on a sheet of paper. If you're fairly confident with your mechanistic skills, and you know how to start it. The beauty about mechanisms is that they help facilitate a logical flow of electrons, a bookkeeping of electrons, and how the bonds are formed and broken. To get you started here, it always helps to draw all the electrons involved. This will help us in the process of understanding where's the nucleophile. Here we are, nitrogen with a free electron pair. We had previously outlined that the carbon is delta plus, so that's our electrophilic center. Once we have an additional bond, we have to break open another bond. Putting in all the electrons now helps you to place proper formal charges. So the negative charge on oxygen, positive charge on nitrogen. If you're struggling there, Chapter 2 is all about molecular representation as well as formal charge calculation and understanding valence, number of bonds that are involved, so on and so forth. I will move on to the next slide. So even though we have acidic conditions, protonation of the carbonyl group is not the first step for imine formation. This is more involved in advanced organic chemistry. Basically, we're protonating this nitrogen, and there is an equilibrium with the ammonium ion. We tend to have a specific range. Amines are bases, and they will consume the proton. And then we form the ammonium ion with nitrogen having 4 bonds. And we are also looking now at which one is more acidic. This one, is, of course, is more acidic compared to this one. But we'll also have a significant amount of amine in our reaction part. So the ammonium ion is not acidic enough to protonate an aldehyde or ketone, but is acidic enough to transfer proton to the negatively charged oxygen in the second step. And here's just a visualization with how the rate is affected. That means, is it going to be fast or slow? There's a particular range, and there's a sweet spot basically between pH 4 and 5. This becomes important when one is trying to carry this out in the laboratory. So here we are, and then you can also practice this with your skill builder segment. So under acidic conditions, aldehydes and ketones can also react with a secondary amine to form an enamine. An enamine is literally that. It's a structure that has an ene component. That is your double bond. So you learned all about that in Orgo 1. And the amine portion is, we still have an amine here. There are 2 dots, or you can draw a line for the free electron pair. Notice that this is going to be done under acidic conditions, so this is going to come from some kind of source. And this is called a secondary amine. Again, we'll look at this in chapter 22. We now have to make kind of an assessment first. Remember how I had drawn this structure close to the carbonyl group? So if I was to do this here as well, let me just try to draw this with my cursor. I'm just going to take an abbreviated carbonyl portion, and I'm going to leave enough space here. We have an R group, we have 2 R groups, R, and then here another R group. And now we have our hydrogen. Similarly to before, we can think about the structural changes as to basically carbon-oxygen bond becomes carbon-nitrogen double bond. So let's just do a little thought experiment, how we're going to eliminate this. How will this change the structure? Let me jot it down. It's always helpful, is something going to happen? Go through the thought process, draw the structure that results from it, and then think about, is that really feasible, or is this just a nonsensical structure and something is really wrong? So if I'm replacing my carbon-oxygen bond with a carbon-nitrogen bond, here we have the 2 R groups. It's not pretty, but here we now see, okay, if I do this like before, I now have a carbon-nitrogen bond, double bond, and there are 4 bonds to nitrogen altogether. Now, it's not very happy in that state. And so there's a second step that happens in which the alpha position, and this will become very important, so I'm giving you another preview, in chapter 21, alpha carbon chemistry, enols and enolates, it's very much related to this. In the alpha position, we have one hydrogen, and that during the process, this hydrogen will be eliminated. So we can draw curved arrows. We're going to make a double bond here, and then we reassign these electrons over here that you will have in the product, and thus you are forming an enamine. So I left out the rest of the structure, but I hope you understand the point I was trying to make. So again, mechanism is identical to imine formation except for the last step. Here, lots of structures. You may need to work your way through this stepwise. Try to be able, mastery requires being able to label nucleophilic attack, proton transfer, and to see the pattern. Remember how I started out? Pattern recognition is our friend here. And guess what? Here's the structure, the kind of shortcut on the previous slide. And then we have something that is basic, something that has an electron pair donor, picks up that proton. Here I did it on the other side, but it's really the same. As we move on through this chapter, basically, as we're looking at pattern recognition, here, primary amine versus secondary amine, we're seeing the parallels. Remember, we had the methyl group here at first, and then this proton is being lost, and we get the imine. And then here we have, using a secondary amine, we get the enamine. And the square brackets, some source of acid. And you can practice this with skill builder, with the skill builder portion as well. So practice the skill. What you want to see here, look at this square bracket, ding, 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 TSOH. This was actually introduced in Orgo 1. Is a source of H+. We're replacing the carbon-oxygen double bond with a carbon-nitrogen double bond. It's a condensation reaction. We're going from an amine, a primary amine, to an imine. Same here, just a different substituent. And then here are a couple of other ones. Here it just gives you a square bracket. We do know that these reactions are acid catalyzed. It's a condensation reaction. See the pattern, loss of water, loss of water. Ammonia will give you the imine. So here I'm just going to focus on the reaction side. Carbon-oxygen bond becomes carbon-nitrogen double bond. And instead of an alkyl group, all we have is a hydrogen. Okay, so it's rinse, repeat once we see the patterns. And organic chemistry starts to make a lot of sense once we have that level of mastery for mechanistic insight and how the bonds change. So, and basically here is another approach to functionalizing our carbonyl compounds. This chapter is focused on ketones and aldehydes. Here is a named reaction. It's a more advanced reaction, but guess what? Acidic conditions. And here we now have hydrazine. The first step is imine formation between the ketone and the hydrazine. And it's going to form a hydrazone, which is shown here. Now, this under these conditions, these are harsh conditions. Basic KOH, potassium hydroxide, aqueous solution, and heat will accomplish the elimination of the carbonyl group. And so we see the two carbon-oxygen bonds being replaced with two carbon-nitrogen bonds, and a stable molecule of nitrogen is also formed in this transformation. So we're looking at converting a ketone to an alkane. So this gives us more flexibility in the toolbox. Here's the mechanism. It may look very weird and very different. If you see the pattern, you know how to approach this. Here's the hydrazone structure that has formed after the condensation reaction. We did it similarly to our reactions between a primary and a primary amine or a secondary amine with a carbonyl compound. So now we have a sequence of where the base is going to rearrange the structure such that, I'm going to fast forward, we increase the bond order between these two nitrogens. That is what we want to focus on. So the shuffling back and forth, proton transfer, proton transfer, proton transfer, gives us the carbon-nitrogen double bond, and we actually are now making it possible in this next step to have a very stable leaving group, basically pushing the negative charge here towards the nitrogen and breaking that bond here, which is then going to be protonated, and voila, we have gone from the hydrazone that was deduced from the cyclohexanone, so the ketone, to now a reduction product. Note the many similarities between the acid catalyzed mechanisms we have discussed. One thing to always note: under acidic conditions, reaction species should either be neutral or have a positive charge. So do not write down anything like a hydroxide anion OH-, it cannot exist in there. We can use water molecules. So that is one of the common rules that we always want to follow.